Hi everybody, welcome to our second lesson in Unit 1A in Chemistry 1. Today we're going to be talking about nuclear chemistry. Okay, whenever people hear this, people's minds go to a lot of sci-fi stuff. But we've got some real practical applications, some real great things that we're able to do practically and scientifically with nuclear chemistry. And there's also some dangers that go along with it as well. So we're going to kind of talk about some of those things today, and also learn to model some nuclear decay processes with nuclear reactions. All right, so nuclear chemistry is basically a subset of chemistry, and it's going to focus on radioactivity and radioactive decay. Also nuclear processes and transformations. And when we say transformations, we're talking about processes where elements actually change their identity by absorbing or releasing particles either from or to their nucleus. We're also going to talk a little bit about nuclear properties and stability of nuclei in nuclear chemistry. So these are the focuses of the nuclear chemistry subset of the larger chemistry realm. If we start with the radioactive decay idea here, you probably first of all need to nail down what radioactivity is. Radioactivity is emission, that's release of energy and particles from unstable nuclei that degrade as they break down. So the idea here is that if you have an unstable nucleus, it might spit out something, it might release something that is going to be maybe one of these ionizing particles, or maybe just some energy. And there's some different kinds of radiation, but anything that comes out of an unstable nucleus would technically be considered to be radiation, and those nuclei that release those things would be considered to be radioactive. Now, radioactivity and stability are kind of opposites of each other, because the less stable a nucleus is, then the more radioactive it's going to be. So the more radiation it's going to release in a shorter amount of time if it's less stable. It's going to stick around for a shorter amount of time and probably decay and release some radiation in the process. Now, if you want to start modeling nuclear reactions, in a nuclear reaction, you're going to see one element maybe transform into another element, and there's going to be one or more particles that either go into the reaction or come out of the reaction. But the big idea that's really important in nuclear reactions is that the total atomic numbers, remember the atomic numbers are the numbers on the bottom of the reaction, and the total mass numbers, remember those mass numbers are the numbers that are on top of the nuclear form of the isotope notation. The totals have to be the same before and after the reaction is over. So, for instance, if you take a look at this example, we've got uranium-238 going into this reaction, and you see the mass number is 238 on this side. Well, being spit out on the other side of the reaction, being formed or produced, we have thorium with a mass number of 234, and we have a alpha particle, a helium nucleus that has a mass of 4 here. And if you look at the total, 234 and 4, this adds up to 238, which is the same as the mass number of the uranium-238 that's in the beginning on the other side of the arrow of the reaction. The same is true for the atomic numbers. If you look down here at the bottom, we've got an atomic number of 92 for uranium. And being spit out of the reaction, we've got thorium with an atomic number of 90, and we've got a helium particle with an atomic number of 2. So the 90 and the 2 add together to make this 92. So this is just kind of like an equation in terms of, the top numbers have to be equal total on both sides, and the bottom numbers have to be equal in total on both sides. So this is super helpful. A lot of times if you've got a missing piece, like there's a blank for one of these 3 things and you didn't know, what goes in the blank, then you just look and see, hey, what's it going to have to be so that the total is going to be the same on both sides. Then you can usually figure out what goes in there. All right, so there's 4 different kinds of nuclear particles. Now, these are particles that are not necessarily just elements that are going in or out of a reaction that are important, that tend to show up. We've got, first of all, alpha particles. Now, alpha particles are basically just defined as helium nuclei. And alpha particles, if you take a look at a helium atom, remember, helium, if you look in the box on a periodic table, has an atomic number of 2 and a mass of, about 4.0 something. So this basically is going to tell you that, you've got 2 protons in a helium nucleus, and you've also got 2 neutrons in a helium nucleus. So the atomic number is equal to 2 because you've got those 2 protons, and remember, together the mass number is the protons and the neutrons added together, and that's 4. So since you got 2 protons and 2 neutrons, then the mass number of a helium nucleus is going to be 4. Now this thing pops up so often in nuclear chemistry. It's got a special name. We call it an alpha particle. It's really just a helium nucleus, but we call it an alpha particle. So people can write it one of 2 different ways. You can write it, with this little Greek letter, lowercase alpha, again with the mass number of 4 on top and the atomic number of 2 on the bottom. Or you can write this as just the element helium with a mass number of 4 and an atomic number of 2 on the bottom. A lot of people choose this way because they don't like to write the Greek letters, but either way is fine with me. Now, beta particles, on the other hand, basically are just fast-moving electrons. And you may be wondering why we're including those things in nuclear particles. Well, the idea is, if you take a look at, something like a neutron, and wonder kind of what is a neutron made of? Well, theoretically, a neutron is an electron and a proton that have been fused together to make this neutron, and that neutron could come back apart into a proton and an electron as well. Usually the electrons are on the outside of the atom, but if you start looking at subatomic particles, you get into up quarks and down quarks and all that kind of stuff. Basically, neutrons have parts too, and one way to think about them is that a neutron is really an electron and a proton added together. So we're going to see these electrons actually go into the nucleus or come out of the nucleus, either by combining with a proton to form a neutron, or that neutron splitting back apart into the proton and an electron again. Now, we call these fast-moving electrons beta particles, and the Greek letter beta is this funny-looking B with the tail on it here. Now, remember, electrons don't have any mass, so that's why the top number is 0. The bottom number is supposed to be the atomic number, which is the number of protons, which is the number of positive charges. Now, electrons have a negative charge, so to get the charge to work out, we actually have to write the charge of the electron down here where the atomic number would normally be. So the bottom number, the atomic number of an electron is actually less 1 proton. It's -1 on the bottom there. If you take a look at the other way to write this, you could just use the E for electrons with the 0 on the top and the -1 on the bottom. Okay, so that's a beta particle. Now, gamma rays are pretty much just pure electromagnetic energy in the form of waves. And electromagnetic radiation doesn't have really any measurable mass, and there's no charge associated with it either. So the Greek letter for gamma is just kind of looks like a Y, but it's really kind of almost looks like a fish swimming down if you were to write it with the 0 mass and 0 charge. These are not really going to affect nuclear reactions mathematically because these zeros don't do much, but oftentimes gamma radiation comes out of nuclear processes along with some other particles. Finally, we've got neutrons. So neutrons are often used in transmutation processes, or captured, or neutron bombardment and things like that. They oftentimes come out of atoms that are being split in nuclear fission processes and things like that as well. So Neutrons have no atomic number, but remember, neutrons do have a mass number of 1 atomic mass unit. So we write that 1 on the top and just an N for neutrons, so that's easy to remember. Okay, these two particles, the alpha particle and the beta particle, are probably going to be the two most important. You may also see gamma rays and neutrons occasionally, but those two are the two that are most important. All right, now, for nuclear processes, we've really got two kind of processes that are opposites of each other. One of those is called a capture process, and one of those is called a decay process. And they're kind of opposites of each other in terms of, in a capture process, one particle is going to be combining with the original element to make a new element. And in a decay process, the original element is going to spit out a particle and in the process turn into a new element. So basically it's which side is the particle going to be on. That's going to determine whether it's a decay process if the particle is coming out, or a capture process if the particle is going in. Okay, so here's an example of a beta capture process. We see some beryllium-7 turning into some lithium-7 here. Now, I probably wouldn't ask you to model this with pictures this way. I would probably want you to be able to write the reaction that would show this. And if you wanted to write a nuclear reaction that looks like this using isotope notation, you'd start off with a reaction that looks something like this. Okay, so you'd have your beryllium with a mass number of 7. Now remember, the top number is the mass number. The bottom number is the atomic number. So if you look on the periodic table, the atomic number for beryllium is element number 4. Now this is a capture process, and it's a beta capture process. And so we're going to combine a beta particle with the beryllium in the beginning of the reaction. So beryllium is going to combine with a beta particle. I'm going to use the little e with a 0 and a -1 for the beta particle. And in the process, it's going to produce lithium-7. So lithium with a mass number of 7 and an atomic number of 3. Now you can see in this process that the whole idea of the total mass number and the total atomic number adding up to be the same total being conserved on both sides of the reaction holds true here, because 7 and 0 before are equal to a total mass of 7 after, and the total atomic numbers 4 and -1 add up to -3. Okay, so that's an example of a capture process where some particle goes into the beginning of the reaction and combines with the original nucleus to make some new nucleus. In a decay process, on the other hand, some particle is getting spit out of the original reaction. So you can imagine this huge chunk of uranium, this uranium nucleus, a piece of the nucleus just flies out. Now this piece happens to be the size of a alpha particle here, so this is an alpha decay process. This is alpha, and it's a decay process because the particle came out of the reaction. Again, you can see the totals add up on both sides. 238 total, 238 total, 92 total, 92 total. Here we've got a beta decay process in the second example here. Iodine is turning into xenon by spitting out an electron, by spitting out that beta particle. Basically what's happening here is one of the neutrons inside the iodine is splitting apart into a proton and an electron. And so when you look over here, we've got, basically this neutron turned into a proton, so we've got an extra proton, and the electron is the thing that actually comes out of the nucleus and is missing from the nucleus from that point forward. Kind of interesting how an element can actually go up in atomic number by releasing something, in this case in this beta decay. Gamma decay, this is not going to be all that important, but basically if you just got an unstable nucleus that has some extra energy, this little star here is showing that this nucleus is excited. Nuclei don't have emotions, but excited just means it has some extra energy, and so this thing spits out a gamma ray. This doesn't show the numbers on the gamma ray. You really don't have to, but if you did, it would be 0 and 0. That's why the mass numbers and the atomic numbers for this thorium really didn't change here in this gamma decay process. Okay? All right, now, The questions you're going to run into probably that deal with, writing nuclear equations, or either you're going to have to write them from a description, or you might have a missing piece in a nuclear reaction that you might have to fill in using the idea that everything has to total to the same thing. And I find that there's some keywords that can really help you out, especially if you're trying to write a nuclear equation from a description. So there's some keywords that can tell you if an element or particle is going into a reaction or coming out of the reaction. So if you are reading a question and it says something like thorium-230 undergoes or experiences a process, then that's telling you that thorium-230 is in the beginning of the reaction. If you see a alpha beta neutron capture, then that alpha beta neutron is in the beginning of the reaction. If one of those particles is absorbed, then that particle is going to be in the beginning of the reaction. On the other hand, if anything is produced, or if this produces something, then whatever is being produced is coming out of the reaction. Same thing if it forms. Okay, produced forms kind of means the same thing. It means that you have that at the end of the reaction. Now remember, a decay process also tells you that particle is coming out of the process. So if it's an alpha decay, the alpha particle is on this side. If it's a beta decay, the beta particle is on this side. Emits is really just another word for releases. So if a particle is released, it's coming out of the reaction. Emits is just another way to say the same thing. Okay, so here's some keywords that you can use to kind of help you if particles are going into or out of the reaction. So these things tell us if it's going in, and then we've got some other things over here that tell us if we've got a particle that's coming out. All right, so in this one here, I see thorium-230 undergoes alpha decay. Okay, so that goes with the thorium-230, and that's going to tell me that the thorium-230 is going into the reaction. So if I wanted to start actually writing this reaction, I'd write my symbol for thorium, which is TH. Remember, if we see thorium-230, that 230 is a mass number, so that mass number goes on top. And the bottom number is an atomic number. So if you look on the periodic table, the atomic number for thorium way down at the bottom is element number 90. Now, if we continue reading here, this says thorium-230 undergoes alpha decay. All right, so I see alpha decay. Decay was over here telling me it's coming out, and this is alpha decay. So that's going to tell me that the alpha particle is coming out of the reaction. Now, I'm going to use the little helium 4/2 for the alpha particle. Remember, that's the alpha particle there. Okay. And it says it also produces radium-226. So produces, again, it means that something is coming out of the reaction. So we're going to have this radium-226 over here as well. So radium-226 over, and then if you look on the bottom, you're going to need the atomic number of radium. If you look on the periodic table, it's an 88. Of course, you probably could have figured that out anyway, because the totals have to add up to be the same total on both sides. 4 and 226 add up to 230, and 2 and 88 add up to 90. All right, so this is the way to write the nuclear reaction for the process that was described here in example 1. All right, in example 2, this says nitrogen-14 experiences, I should have said experiences. Let's get rid of that. Nitrogen-14 absorbs a beta particle to form carbon-14. All right, so nitrogen-14 is the beginning element here. Now, there's no keyword that goes along with it, but you can see that we're forming carbon-14 at the end. So, the carbon-14 is coming out of the reaction here. So nitrogen-14 is going to be in the beginning. We're going to start off with our nitrogen with a mass number of 14 and an atomic number of 7. And it says it absorbs a beta particle. Now remember, absorbs was in the beginning here as well, so I was too quick to write my arrow there. If this says absorbs a beta particle, then that beta particle must be going into the beginning of the reaction. So we're going to go ahead and put our beta particle, which if you remember was the electron with a mass of 0 and an atomic number of -1, also with the nitrogen on the left side of the arrow. All right, and we can go ahead and draw our arrow here. We're forming carbon-14 here. So Remember, forms means it's coming out of the reaction. So the carbon-14 is going to be over here on the right side of the arrow. And mass number of 14. You can look on the periodic table and see what the atomic number of carbon was. It's a 6, but you could have added it up as well. Even if you didn't know what element came out here, you know that 14 plus 0 has to add up to 14, and 7 plus negative 1 has to add up to 6. And that 6 would have told you that was carbon, even if this example didn't tell you that. So sometimes you're going to just have to kind of fill in the blank or figure out what new element or what new nuclide is produced when these processes happen. So a couple of examples there that kind of use some of those keywords. Before we go any further in here, I'm going to and do a couple more examples just because I don't think those two are quite enough. Let's take a look at this. This is just a worksheet on nuclear equations that is kind of useful here. So here's some processes that have a missing piece in the nuclear equation, and you've got to try to figure out what this missing piece is. So these are probably kind of the easiest questions that you might have to answer dealing with these kind of problems. And again, you're just using the idea that the things on both sides of the arrow have to add up to give you the same total on both sides. So for instance, let's take a look at number 4 here. I've got a missing piece on the left side of the arrow, and on the right side of the arrow, it looks like I've got an electron and this vanadium-52 nuclide. So since everything has to add up on both sides of the arrow, just literally go ahead and start seeing what's the total on the side that you have all the information for. So 0 and 52 means that the top number that would have to go in this blank would be 52. And the bottom number is going to have to be equal to the total here, and 23 and negative 1. Remember, when you add a negative 1, it's like you're subtracting 1. So 23 and negative 1 makes 22. And if you look on the periodic table, the 22 will tell you what element it is. And element number 22 on the periodic table is titanium. So that's how you could figure out what the missing piece in a nuclear reaction would be. Okay? Now, sometimes your missing piece is an element with a certain mass number. Sometimes your missing piece might be a particle. Let's take a look at number 6 here. This says bromine 85, and doesn't give us an atomic number in the bottom, makes something, and krypton with, we don't know what this atomic number is, and a gamma ray. Now, the gamma ray is not going to be super important here because, the mass number and the atomic number is 0. But if you look, again, the same thing has to be true. The totals have to add up on both sides. Now, I think the first thing I would do would be to try to figure out what's the missing piece in terms of the atomic numbers for the bromine and the krypton, because remember, atomic number has to match the identity of the element. So mass number for bromine doesn't always have to be 85. This number can be different. That's why I gave it to you. But the bottom number, if you look on the periodic table and see what the atomic number is for bromine, that's not going to change. And on the periodic table, the atomic number for bromine is 35. So we can go ahead and fill that in. We know that bottom number for bromine is going to be a 35. You can do the same thing for krypton. Krypton is number 36. Element number 36. So we know that bottom number's got to be a 36. So when we start looking at, okay, now we have all of the missing information except for what goes in this blank. Well, 0 and 85 add up to 85, and you'd have to add one more thing to equal 85. Well, this is already equal to 85. So 85 plus 0 would have to equal 85. And if you start looking at the bottom number, what and 36 is going to make 35? Well, -1 and 36 is going to equal 35. So this must have been, if you look at the numbers, 0 and -1. This is not an element. This is one of those particles that we were talking about. This is a beta particle. This is an example of a beta decay reaction. Actually, both of these reactions are beta decay reactions because the electron came out of the original nucleus in the beginning. This one just happened to have some gamma rays coming out as well, but again, that didn't really affect the math too much. Now, if you take a look at some of these other ones here, you're going to have to write a nuclear reaction that is based on a description. Okay, and sometimes you might not even have all of the information that you need in the description. There may be a missing piece that it doesn't talk about. So, even if you've included everything that's listed in the description, you want to make sure that, both sides add up to equal the same total. So let's take a look at, something like, number 13 here. All right, so this says uranium-238 undergoes an alpha decay and produces 2 gamma rays. I'm going to zoom in on this just to give me a little bit more room to work. Okay, so this number 13 is the one I want to do here. All right, so if uranium-238 undergoes a process, you might remember that means that it's in the beginning of the reaction. So my uranium with a mass number of 238 is going to be in the beginning of the reaction. Now, it doesn't give me the bottom number, but remember, the element can give you the bottom number. So if this is uranium, you can look on the periodic table and see that that element is element number 92. So we're starting out with uranium-238 over 92. So it undergoes. Now, this says undergoes an alpha decay. Remember, decay is something that spits out whatever particle we're talking about. So in this reaction, we're spitting out an alpha particle. So that tells me the alpha particle is coming out of the reaction. So here we've got a helium nucleus that's coming out of the reaction. It also says it produces 2 gamma rays. Now remember, a gamma ray was this thing that had no mass and no charge. And you could do, plus one of these and plus another one if you wanted to, or you could put a big 2 in the front. Doesn't really matter. You could put a coefficient of 2 to say that you have 2 of them. That would be fine as well. Okay. Now, if you start looking to make sure you're not breaking the cardinal rule here of the totals have to add up to be the same total on both sides. You can see, hey, I got a whole bunch of stuff over here, 238 and 92, and not much over here. There's got to be a missing piece that was not in this description. This doesn't talk about another element besides uranium, but there's got to be something there because the totals have to add up to both sides. So this thing spit out some energy and spit out a helium nucleus, but we got to figure out, what new element was created as well. So if you go back to the idea that, hey, the totals have to add up to be the same total. So the zeros don't do anything. So 4 and what makes 238? Well, subtract 238 minus 4. 4 and 234 is going to add up to give you the same total mass number on both sides. You do the same thing with the atomic number. 2 and what is going to make 92? Well, 2 and 90 is going to make 92. And that bottom number tells you what new element you created. This is element number 90, which has to be thorium. So in this process, uranium transformed into thorium by spitting out an alpha particle, an alpha decay process. Okay. We also just happen to have some gamma rays that went along with it. All right, hopefully that helps you write nuclear reactions effectively. It's a pretty easy concept. Just, make sure that you memorize what each of those 4 particles are. Okay, so that's super important in terms of making sure that the formulas and the mass numbers of those 4 different particles. I would also kind of recap the keywords that tell you if things are going into or coming out of a reaction. That's super important to make sure that you know. And then again, the big idea that everything's got to add up to be the same total on both sides of the reaction. Those big ideas will pretty much help you write any nuclear reaction that you need to write.